Hello and welcome back. So in this video we will look at probability distributions, notably Bernoulli and Gaussian distribution. All the slides were provided by Dr. Christopher Bishop based on his textbook PRML, the Pattern Recognition and Machine Learning textbook. So we will first consider the Bernoulli distribution, which deals mostly with binary variables. It is basically these are two states, either 0 or 1. Okay. So if you have a feature which can take either of two values, that would be a good example of a binary random variable. Okay. So just to have an example, we consider a coin toss experiment with a damaged or a biased coin, which means that the probability of either getting heads or tails is not the same. So maybe there is higher probability of getting a head than there getting a tail when you toss it. Okay. So the we will consider the random variable x, which is linked to the event heads or tails. Okay. So, and depending on the event x will take a certain value. So, if heads, if you toss the coin and you get heads, x gets a value 1, and if you toss the coin and you get tail, x gets a value 0. Okay. So, such a variable x is referred to as a binary random variable, and it is either associated with the with you getting either heads or tails based on a coin toss. Now, what we do is we will assign a probability with that event. So, since this is not a unbiased coin, this has a bias, we will say that the probability of getting a head given one coin toss is given by the value mu. Okay. So, mu denotes the probability that if you toss the coin once, the probability of getting a heads is mu. Okay. And this is a notation. So, this mu is the parameter for the Bernoulli distribution. Right. So, if the probability of getting a head is mu, okay, what is the probability of getting the tails would be, since heads or tails they are mutually exclusive, will be 1 minus mu, right. So, given a coin toss event, if you want to predict the probability of getting either a heads or a tails, then this can be given by this cumulative expression. So, which is basically probability of x given mu, where x is the event heads or tails, is given by this expression mu raised to x 1 minus mu raised to 1 minus x, right. So, how does this work? Because if x is heads, if x is related to heads, then x equal to 1. So, the probability of x equal to 1 given mu would be, it will just be mu times 1 minus mu times 1 minus 1, which will be just mu, which is correct, right. And the probability of x equal to 0 given mu is mu raised to 0 times 1 minus 2 mu raised to 1 minus 0, which is 1 minus mu. Okay. So, that is correct. So, the probability of getting a heads or a tails is what this, if you want to link it to some experiment that way, is given, this is what it denotes. The mu is the parameter for the Bernoulli distribution. So, you have to in the problems where we define where we are dealing with this probability distribution, most of the time the problem will be about estimating mu, that is what we will be doing most of the time. So, given mu, we know we can now formulate the expression for getting a heads or a tails. So, probability of x equal to 1, probability of x equal to 0 given mu. The average value of mu of x is mu. Okay, we will see that with a small example sometime later, and the variance of x is mu times 1 minus mu. Okay. So, these two you can actually calculate based on your formula for expectation as well as the variance, right. We will look at more concrete examples later on, but this is just an introduction to the probability mass function for the Bernoulli distribution, right. So, this is given by mu raised to x times 1 minus mu raised to 1 minus x, where x is the event, x can be either 1 or 0 depending on heads or tails. Okay. So, it is just not for a coin flip, wherever you have any variable that you can associate with like one either or choice, like there are only two choices for that variable can take, then you can associate a Bernoulli random variable with that quite easily. Okay. So, the parameter estimation for the Bernoulli distribution, So, it is called the maximum likelihood technique. We will see what that is again later on, but just if we can from a common sense point of view, we should be able to follow this argument. So, we have a set of these events. So, let us say capital N coin tosses, okay. So, out of which we get m heads and n minus m tails, okay. This is the total thing, okay. So, what is the probability of observing this sequence of m heads? So, this m heads and n minus m tails, okay. This is what is denoted. So, probability of observing the data set given that the probability of heads is mu, okay. This is the conditional probability. Is basically, since each of these events is independent, we just have to do the product of the of each of these probabilities. So, that is what this expression does. So, since you are doing n coin tosses, then for each coin toss, what is the probability of observing the head? That is probability of x given mu, and so since there are capital N coin tosses, you just multiply all of them, that is what gives this product, and then instead of probability of x given mu, we substitute the expression here, which we saw for the probability of probability mass function for Bernoulli distribution. So, recall that probability of x given mu is mu raised to x times 1 minus mu raised to 1 minus x. Here we have n sequence of n coin tosses, capital N coin tosses. So, for each coin toss we can write this as a probability. Since there are capital N coin tosses, each of them being independent, we just take a product. So, this symbol here represents the product, okay, of n capital N terms, okay. From a computational point of view, it is since multiplication can lead to some of these numerical errors, if you take a log of this expression, since you take the log of products, then it decomposes into a sum of the logs, okay, because you can take the logarithm, you can take the if you take let us say log of let us say 2 a times b is log a plus log b, you can do that, right. So, that is possible. So, that is what we have done for each of those terms. So, that is the expression right here. Taking the log of this product decomposes it into this sum, right. Then if we substitute the values in here, we can expand it in this fashion. So, if you want to write it down in a concrete way, so log of the products n equal to n capital N terms mu raised to x n 1 minus mu raised to 1 minus x n. So, the log of this entire expression. So, this is a product of capital N terms. So, we can write this as a sum of capital N terms by taking the logarithm inside. So, that we will get summation over n equal to 1 to n. So, the log of mu raised to x n is, you will get x n log mu, right, plus, so these are products, right, you can this will become a summation here, plus 1 minus x n log 1 minus mu, right. So, the summation is for this entire term, okay. So, this is a simple thing of writing the logarithm of products as sum of logs, okay, that is what I have done. So, then if you want to estimate mu, you can set the derivative of this log p du to 0 with respect to mu, and then you can calculate mu ml as the total number of heads divided by the total number of tosses, okay. So, m is the total number of heads, okay. So, you might wonder why would we consider this expression and why do you want to take the derivative of this. So, you can consider this log p du like a loss function, okay. So, how is a loss function? So, we formulated this probability of capital D given mu, but probability of capital D is your data is basically the sequence of coin tosses. What is the probability of observing these coin tosses given this Bernoulli parameter? That is what this expression evaluates to, right, because each coin toss is independent of each other. We write the probability of observing the data as the probability of observing x1 times the probability of observing x2 times the probability of observing x3, so on and so forth up to the probability of observing x1. So, it is the product of all these terms, each of the probabilities. So, but then we know the expression for the probabilities is a Bernoulli random variable x. So, we can plug that expression in there and the rest is just algebra. So, now we have got the probability of observing this data set, that is this sequence of coin tosses given given this mu. Now, what we want to do is we want to maximize the probability of observing this data set, right. So, that is the idea behind constructing this probability distribution. So, if you want to maximize the probability of observing the data set, it is the same as maximizing the log of the probability of observing this data set with respect to mu, the parameter that you want to estimate. So, by taking the derivative with respect to mu of this function, this log p du, then you can calculate mu ml. So, this is referred to as this log of p, this term is always refers to as the log likelihood, and this p of d given mu is referred to as the likelihood. What is the likelihood of observing this data set given this parameter mu? So, this is a Bernoulli trial, sequence of Bernoulli trials, and it is characterized, we know that we assume that it is characterized by this mu, which is the probability of observing x equal to 1. Okay. So, we then construct the probability of observing the entire data set, which is x1 to x1 through xn. We assume that each trial is independent of each other. So, it is just the product of the probabilities of observing each individual trials, that is what is given in this expression, and you just have to plug in the formula for p of x given nu for a Bernoulli distribution, and then take the log, because then it is easier to process that way, and then differentiate this log with respect to mu and set it to 0, and that will give you the expression and from there you can derive this mu ml. I have not gone through the algebra, but it is not too hard to do. Okay. So, this expression, this probability of observing the data set given the parameters of your distribution is referred to as the likelihood, and this taking the logarithm of that is usually referred to as the log likelihood. Okay. Now, we will consider another distribution which we will often be using from now on. It is known as the Gaussian distribution. Here again the form of the distribution is given here. If you are not familiar with it, you just familiarize yourself by just going through this expression. This sigma is the standard, sigma squared is the variance. Again note that this is for a one dimensional variable. So, x is a one dimensional variable and we are looking at one x, and sigma squared is the variance, mu is the mean of the distribution. Okay. And what does this expression evaluate? So, if we have a value x of that event, the value that, so this is for continuous variables. So, if you have a value x, this expression will evaluate the probability of observing x. What is the probability of getting x? Okay. So, what is plotted here on the graph is the graph of the probability distribution, wherein the x axis is x and the y is the probability of observing x. Okay. And the mean is at mu. This width of this distribution is 2 sigma, where sigma is the standard deviation, sigma squared is the variance. Now, if you are not sure as to like okay, where do these things, what kind of variables lead to this kind of distribution? Okay. So, just to give a practical example, let us consider, let us say a class with like hundreds of students, okay, and then they take an exam. So, you get the marks for every student. So, we have a student serial number, I will just have a table here. Okay, serial number of the student and then marks. Okay. So, each for that particular test. So, the student serial number goes from 1 through let us say 100, and the marks also will also go from in this case let us say they go from again 40 to 100, and everybody passed. Let us say we have a hard threshold of 40 and everybody got over 40, you can imagine it that way. So, marks will go from let us say 41, 41.5, so on and so forth. Let us say nobody got less than 40, let us say something like that. Okay. And then somebody could have gotten 100, so on and so forth. Okay. So, this is our data, we have about 100 students and the marks in an examination. So, what you do is you construct a histogram. How do you construct a histogram? So, let us take an axis, this is marks, okay, and it goes from, just for the sake of convenience, you have 40 to 100. Okay. So, the way to construct an histogram is you count, you make the bins on your axis. So, we will make bins of size 5. So, 40 to 45 is one bin, 45 to 50 is another bin, so on and so forth, okay, up to 100. Okay. So, what you do is you count the number of students whose marks fall between 40 to 45. Okay. Let us say some number, this axis is the number of students. Okay, this is the number of students. So, you count the number. Okay. So, you do that for let us say all of them. Typically what you will get will be something along these lines. I am drawing it smooth. So, you will get something like this. Okay. So, you make bins of size 5. So, 40 to 45, what are the number of students who got marks between 40 to 45, what are the number of students who got marks between 45 to 50, so on and so forth, and you just plot it as a histogram, wherein the x axis gives you you can plot with the center of the bin. So, instead I have just indicated here as 40 to 45, instead of doing that you can just say 42.5 and plot that number, 52.5 and plot that number, so on and so forth, or 47.5 and plot the number of students between 45 to 50. So, you can plot that and you get this histogram. Okay. And if you normalize the y axis here, the number of students by total number, what you get is the probability distribution of the marks that the students scored in that particular examination. Okay. So, it is a summary, it is a good way of summarizing what your class performance is like. Okay. So, you can easily say, so if you can let us say somebody gets 40 marks, you can plug that and see whether he is one of the few students, what is the probability that he got, how far away he is from the mean, things of that sort. So, to summarize the statistics of a class, this is a good way of doing it, because then you can easily assign grades using this. Okay. That is one of the things that people do. Usually they calculate this curve and use this curve to assign grades, right. So, the mean, this is the mu. We will see how the mean and standard deviation are estimated for a Gaussian distribution. It is something that is very familiar to you, but the assumption that you are making every time you do this calculation is that you are assuming that your that the data falls under a Gaussian distribution, right. So, for I am giving you example of marks, you can do that for let us say you measure all the heights of all the students in your class. Okay. You have a class of 100 or several hundred and you measure all their heights, and if you plot again a histogram of heights based on some bins, then also the distribution will look very close to a normal distribution, or for that matter many of the quantities that you measure might look like a Gaussian distribution, because any calculation that you usually do makes this assumption. We will see what those calculations are. So, this is in 1D. Okay. This is the for a 1D example, one dimensional example wherein you have marks. Okay. Sometimes the variable x you are looking at is multidimensional, let us say of dimension you are all used to dimension small n, okay, small n, but for the purposes of this lecture I am going to use capital D. Okay. So, if you have if your dimensionality of x is capital D, okay, so it has let us say x has many features, that is one way of looking at it, right. If x has many features, then x would be some vector of length d, x is a vector of length d, this mu will be a vector of length d, because each dimension will have its mean. So, mu will also be of length d. This sigma is called the covariance matrix, and it has size d cross d, okay, and this is the modulus is the determinant of the covariance matrix, square root. Okay. So, this is the determinant. Okay. So, this is for a multi-dimensional x, this is how the Gaussian distribution formula is like. Okay. So, what I have plotted here in this figure basically is the, let us say if d is 2, okay, d is 2 variables x1 and x2, okay, and these red lines are contours of constant probability or constant probability mass function. So, for instance, if you plug in these x1 and x2, find out all values, find out the range of all values of x1 and x2 for which n is similar or same, then you can plot this, the locus of all those x1 and x2 is basically this. Okay. So, what it shows is that x1 and x2 are correlated slight kind of, right, because x1 seems to x2 and x2 seems to linearly increase with x1. Okay. So, these plots are that way useful to figure out whether there is correlation between your variables when you have when you have multidimensional variables, when you are dealing with multidimensional variables. Okay. So, this is the general form of the Gaussian distribution. So, this exponent, it comes in the exponent. So, you will be typically you will be writing it as something like this for one dimension, and you will have 1 over square root 2 pi sigma, okay, the normalization constant, all right. So, then for a Gaussian parameter estimation, how do you, so remember we saw for Bernoulli distribution we estimated, we looked at how we can estimate the Bernoulli parameter mu, which is the probability x equal to 1, right. So, how do we do the similar thing? So, because we have the normal distribution, it is also called normal distribution or the Gaussian distribution is denoted, has two parameters mu and sigma squared. So, we want to estimate mu and sigma square, how do we do this? Okay. So, typically, so recall that this is for continuous random variable. So, x can take any real value, but usually data is discrete, right, we only observe for specific x, right, that is the thing. So, we then again once again what we do is for based on the observation. So, these blue points are the observations we have. So, based on this observation we calculate the probability of observing the data or the likelihood of observing capital X refers to the data that we have observed. Let us say we have capital N points. Once again, like we saw in the Bernoulli distribution, the probability of observing the data set is the probability of observing each one of the individual data points, and we know that the probability of observing each data point is given by the normal distribution. So, the total probability of observing this data set is the product of each of the individual probabilities, which is what is given by this expression. Okay. So, then what we do is, so similarly we take the log of that likelihood and the log of the product transforms to summation of the logs, which is what is given here. I urge you to actually work this out yourself, because it is very trivial algebra, but it will also be comfortable with the expressions here. Now, once we have this expression, what we want to do, like we saw earlier, is to maximize the log likelihood of observing the data, right. What would be the, that is what we mean, mu and sigma squared should be such that the probability of observing this data is very high. Then the way to do that would be to take the derivative of this expression. So, d delta over delta mu of log of p x sigma squared, set that to 0, and then you will do delta over delta sigma squared of the same, I would say delta sigma, sorry, set that to 0, and then once you solve for it you get two results, which both of it should not surprise you. It says that the mu ml, it's called, this is called the maximum likelihood technique. Mu ml is nothing but the average of your data points, okay, and your sigma squared, which is the variance, this parameter in the Gaussian terminology is called variance. This is nothing but the, you calculate the variance of your data given mu ml, that is what you get, okay. So, which is basically the mean of x minus mu ml squared, that is the mean of x minus mu ml square is the sigma squared value here. So, this is typically the statistics that you always calculate, right, whenever you have any data set, or you are like, oh, we will characterize it by using the mean and standard deviation. When you do that, what you are assuming is that your data comes from a normal distribution, that your data set comes from a normal distribution, and these are the assumptions that you are implicitly making when you calculate mean and standard deviation. The assumption being that your data is normally distributed, that they are drawn from this normal distribution with a particular sigma and particular mu, okay. So, when you come in the context of machine learning, what we will again, we will model data using these distributions. So, for instance, where we have problems which involves 0 or 1 choice, we will use the Bernoulli distribution, and where problems that are continuous variables involved, we will use the Gaussian distribution. And the problem, you will see that the problem, and I will explain this in a later video, we will see that what we are trying to do is to, we will end up modeling this mu using our data, and that model and using, and for instance even linear regression can be brought in this form, we will do that in a video soon. So, we end up modeling, or we are trying to estimate this mu, sigma, or in the case of the Bernoulli distribution, again the parameter Bernoulli parameter mu, those are what we try to estimate every time, Okay. That is the output that we are looking at, and implicitly, and we this what I wanted to show with this video is that typically for a given data set, how do you calculate mu and sigma. Okay. This is done implicitly in many of the models that you are using. We will see that in a later video. So, for a if you want to consider a multidimensional data where each of the x1s have, let us say, d dimensions, okay, the procedure is the same. So, we still construct the log likelihood of the data given a data set consisting of n points, and each of the independent and identically distributed, that is what IID stands for, independent identically distributed. So, the probability of observing x1 times the probability of observing x2 times the probability of observing xn. So, for all the n data points, the product of each of these probabilities is the probability of observing the entire data set. Okay. And we do that like we did it for the one dimensional case, and we can still do the log of the probability, and you will get an expression like this. Once again, you can take the derivative with respect to mu. Remember, now mu is a multidimensional variable, and we also take the derivative with respect to each of the component. Again, sigma is a matrix here. So, it has d into d plus it has d square elements. Okay. So, once we do that, we can do the similar process wherein taking the derivative with respect to mu and this capital sigma, set it to 0 to obtain the value of x and sigma. Okay. In this context, we will remember this, in order to describe a Gaussian probability distribution, in order to estimate or calculate a Gaussian probability distribution, we just need two quantities. One is this, remember, we just need the mean and the variance. Okay. So, these are referred to as the sufficient statistics. Okay. You recall that, right. So, because you do not need all the data points. In fact, that is one of the reasons why we construct this probability distribution. If you have a very large data set, you can actually summarize the data set with just 2 parameters. In the one dimensional case, it is just mean and standard deviation. In the multidimensional case, you will have more than that, because remember, this is a d cross d matrix. So, you will have d means, right, because each dimension has a mean, feature has a mean, and this will turn out to be a symmetric matrix. So, you will have d into d plus 1 by 2 parameters, independent parameters, right, because if it is a symmetric matrix, these are the unique d into d plus 1 by 2 unique elements of sigma. Okay. So, it is still a lot. Remember, if there are 100 features, that is a lot of parameters to estimate. So, typically what when you are solving these problems using probabilistic techniques, what people usually do is to assume that d is diagonal. Okay. So, that is the, so that you have only d parameters to estimate. In fact, you can even they assume that u d is given by some sigma squared times identity matrix. So, then you just have again only one parameter. Okay. So, so depending on how you model, you can reduce the number of parameters you would like to estimate using when you are using a multidimensional Gaussian. Okay. So, reiterate, you will set the derivative of the log likelihood function to 0 again with respect to mu, and you can actually solve to obtain that for mu again for the multidimensional case is the mean of your data points. Again remember that these are vectors. So, for every dimension you have to independently calculate the mean, and once again the covariance matrix is given by this expression, the average of the expectation of your this term here, x minus mu ml times x minus mu ml transpose. Again remember, x and mu are vectors of dimension d. Okay. So, so we have looked at two distributions, Bernoulli and Gaussian. Bernoulli distribution is used to describe variables that can take 0 or 1 values. Okay, a typical example is coin toss. So, it has only one parameter which is basically the probability of observing x equal to 1. Okay, x equal to 1 might correspond to any event, like for instance, the event we have talked about, this is the coin toss wherein x equal to 1 corresponds to heads, x equal to 0 corresponds to tails. So, what the distribution is characterized by probability of x equal to 1, which is given by mu, and we also saw how we estimate mu. Mu is just the number of, if you are given n, a sequence of n coin tosses, we just calculate the total number of calculate the number of coin tosses where it landed as heads, which corresponds to total number when x equal to 1, and the ratio of the total number where x equal to 1 divided by the total number of actual coin tosses, this gives you the estimate of mu there in the Bernoulli distribution. For the Gaussian distribution, there are two parameters, one is the mean and the standard deviation or covariance in higher dimensions, and the mean is basically the mean of your data points, observed data points. Remember that you have to take the mean across every feature independently, and the covariance is nothing but the covariance of x, again it is 0 centered. So, x minus mu ml times x minus mu ml transpose, the mean of this value is your covariance matrix. Again remember x and mu are again d dimensional, where d is the dimensionality of x. Okay. So, subsequent to this we will look at various techniques, leftover techniques for in machine learning. We will look at SVM, we will look at naive Bayes classifier, and then we will move on to maximum likelihood estimation, how would appraise, let us say in linear regression, then maximum a posteriori methods, and then finally Bayesian regression. We might postpone Bayesian regression to the next week, but maximum likelihood estimation and map techniques we will look at this week. Thank you.